All right, what's going on, folks? So today, what you guys are going to be doing, and I wish that I were doing it with you, but this is the best way that I can think of to take notes. So everybody should have one of these. This is going to be our ray diagramming in-class practice, and then the second page is going to be our ray diagramming homework assignment. So I'm going to take you through the first six, and then we're going to fill out some notes as well. And then you have to do the next six for your homework assignment. So the first question that I've got for you guys is, do normal mirrors make a real or a virtual image? So we talked about this in our lab the other day, and a virtual image is going to be an image that is not going to be projected or taking place in the real world. So if I were to take a look at a ray diagram of a normal mirror, maybe, there it goes. We've got the object over here on the left-hand side. And that object is going to be then casting light rays into the mirror, which then reflect off. All right. And those light rays, when they reflect off, they don't meet at any point. So what happens is we extend those light rays into the mirror, into what's called the virtual, or I call it imagination land. And then we have an image that is going to be shown on the opposite side of the mirror. Now, obviously, there's not an image on this side of the mirror. What we have is we have an image that is actually located inside of the mirror. So is it real or virtual? Well, it's going to be a virtual image because it's not something that can then be projected to the other side like we were doing in our lab. Is it upright or inverted? When I'm looking at these rays, they're going to match up so that my arrow's pointing up. So it's going to be upright, and then size, it's going to be the same size. So that's how a normal mirror works, or we call that a plane mirror. But we have other kinds of mirrors as well. So we have what are called convex and concave, which we'll talk about in our notes in just a second. So a real image are formed by reflected or refracted light rays and can be projected onto a screen. So something that can actually be seen. Whereas a virtual image are formed by those virtual rays extending into the mirror or into that virtual world or that imagination world. So we've got two different examples here where I've got a real image and I've got a virtual image. So we're going to fill out this chart, and this should be a document that you got from the sub as well. And as we're going through here, this is going to be kind of like your summary guide to make sure that you understand, hey, for a plane mirror, do we have a real or a virtual image? Is it upright, is it inverted? Is it reduced, is it enlarged, is it the same size? So obviously for this plane mirror that we just did, we have a virtual image. It's going to be inside of the mirror. It's going to be upright. It's not flipped. And it's going to be the same size as the original object. So we have concave mirrors, and this is what we were dealing with in our lab the other day. And these mirrors focus light to a certain point, and that point is called the focal length. So anytime a ray comes in, no matter where it hits on that mirror, it's going to bounce into the focal length. And we find these in things like reflecting telescopes, auto headlights, because we want to be able to see objects in enlarged states, and that's going to be easy for us with a concave mirror. And then ladies, your makeup mirrors, those are going to be an example of a concave mirror as well, so that you can very closely see like your pores, and there's an enlargement of the image depending on where you are compared to that mirror. So what I want you to think about with these concave and convex mirrors, they're just a reflecting sphere. So here I've got a circle, and again, imagine that this is a three-dimensional shape, but I've got a center of the circle. And if I were to draw a line directly through the center of the circle, and then erase a piece of that circle, what I have here is a segment of that sphere that has what's called a focal length. And that focal length, sometimes it's seen as F, sometimes it's seen as C over 2, C being the center of the circle. But the relationship there is that the focal length is going to be 1/2 of the radius of the sphere. And then we have the concave side. I like to think about it like you're driving into a cave. So if I'm going from the left to the right, it looks like I'm going into the cave. And then I've got the convex side. So either side is going to be reflective, and we're going to do ray diagrams with both. So here I've got a couple of different things labeled. And with these ray diagrams, a curved mirror has a geometric center. That's going to be that center point from the concave side. It has a center of curvature. Okay, I'm sorry, the geometric center is right here. And then the center of curvature is going to be the center of that sphere. And that has a radius of curvature, which is the distance from the geometric center to the center of curvature. So this length right here, basically the radius of the sphere. And then we have what's called the focal length, and that is the distance to the focus from the mirror. So any light that bounces in will go through the focal point, okay? The way that it works is that sphere, any angle of incidence, the angle of reflection, will then point that light ray through the focal length. So I've got an object here. I've placed it in between the center of the circle and the focal length. And when we're doing ray diagramming, we're going to follow basically two simple rules. The first ray is going to be drawn at a parallel line until it hits the curve of the mirror. Then it's going to bounce, and if I were to zoom in on that mirror, I can show that the angle of incidence compared to the normal and then the angle of reflection will always bounce through the focal length. So it's going to come in parallel, bounce, focal. So it looks like this. It goes in parallel, and then it bounces and goes through the focal point. So then we've got a second ray that has to be drawn. Remember, anytime that we need an image to be shown, we have to have those two rays are going to be intersecting at some point, and that's going to help us to determine where our object is, what it looks like. So my second ray is going to be drawn through the focus and then parallel. So I draw it focal, bounce, parallel. So it looks like that. We're going to do a lot of ray diagramming in this tutorial, so you're going to want to make sure that you have a straight edge, pencil, something like that. But then I have this intersecting point right here, and that's where I'm going to put, where the intersection is, that's where I'm going to put the top of my object. So I've got the top of my object is what is reflecting these lines. So then the top of my object is where the intersection happens as well. So find the intersection, put the top of your object there. So if this were a candle, the flame of the candle would be put right here. And what we'll see is that the object is actually inverted. Okay. So again, this is just a real quick demonstration, kind of show you draw a line from the top through the focal, draw a line through the focal, parallel, and you'll get an image that's going to show up at the intersection point. Now, if there's no intersecting point, there's no image. If there's no intersecting point on the left side of our concave mirror, maybe there's one on the right side in that imagination land, in that virtual world. We just have to extend our rays. So we'll do a couple of different examples, and I'll tell you guys to kind of pause, and this is going to be an Edpuzzle, so I'll have some questions that I ask you guys as we're going. So our first situation, this is going to be the first one on the in-class practice. So you're going to want to do this with me. Our first ray is going to go parallel, bounce, focal. So it should look something like this. Parallel, bounce, focal. And then our next ray is going to go through the focal, straight line, bounce, parallel. Through the focal, bounce, parallel. So then we have our object that's going to show up, and it's going to be real, inverted, and reduced. So this is obviously a smaller arrow than the original image. It's real because it is on the left-hand side of our concave mirror. It could be projected. It's inverted because the intersecting point was at the top on the original image. Now it's on the bottom of our projected image. And it's reduced. It's no longer that large. So this is an easy one. I'm going to kind of ask you and prompt you to do this ahead of me and answer some questions on the Edpuzzle. So we'll go ahead and we'll fill out our chart here. When we have a concave object, okay, or a concave mirror, where the object is greater than the center of curvature. So it is located farther away than the center of curvature. If the center of curvature we're at 10 centimeters, maybe this is at 12. So I'm going to have a real object or a real image that is inverted and reduced in size. So our next one is going to be when the object is at the focal point. Actually, it's the one on this homework assignment is going to be at the center of curvature. So first ray, parallel, bounce, focal, parallel, bounce, focal. Do this on here, question number 2. And then the next ray is going to be drawn through the focal, bounce, parallel. Through the focal, bounce, parallel. Now we've got an intersection here, which means that it's on the left-hand side of the mirror, so it's going to be real. Is it going to be upright or inverted? It's going to be inverted because the top of my object is going to be the lowest point. And then it's going to be the same size. So when I look at it, this is going to be the exact same size arrow. It's just inverted, and it's located at the same point. So if my center of curvature is 10 centimeters, the object will be located at 10 centimeters as well. And we saw this in the lab. So here's number 3, first ray, parallel, bounce, focal, parallel, bounce, focal. So now I'm going to have my object is in between my center of curvature and my focal length, but the same rules apply. And then my next ray is going to go through the focal, bounce, parallel. Through the focal, bounce, parallel. So now I've got this intersection over here on the left-hand side. It's on the left-hand side, which means we can project that image onto a piece of paper like we did in the lab. That means that this object is going to be real. The intersection point is down here below the primary axis. So that means that the object is going to be inverted. And then it's going to have a larger body, right? So this is going to be small. When I draw the image, it's going to be a much larger image. So it's going to be an enlarged object. Okay, so that was the third one. Now our fourth one is going to be at the focal length. So this is it. And then we're actually going to put this into our notes table as well. So here we go. We're going to draw our first line, just like always. Through or parallel, and then through the focal length. Parallel, through the focal length. But now we got a problem. Our second line is supposed to go through the focal length. If we're on top of the focal length, can't really do that. So what's going to happen? We're actually going to create a new rule. If this is this case where our object is sitting on top of the focal length, we're actually going to go here, okay, to that point A. So we're going to, if we can't go through F, we're going to bounce to here, and then we're going to bounce off at the angle of reflection. Now, what do you notice about these two lines? If I zoomed out and out and out and out and out, would there ever be an intersection? No, because these two lines are parallel. So because these two lines are parallel, we'll have no image because the lines are parallel and they never intersect. So we'll fill that out on our table. No image, no image, no image. And I did that demonstration in class. I brought that concave mirror closer and closer and closer and closer and closer to you guys until you blew up to this really large image, and then there was no image. And then as it kept getting closer and closer, you as the object getting closer and closer to the mirror, what happens is you show back up, but you went from being inverted to right side up. So when we finish out the rest of this table for our concave mirrors, I bet you can predict what's going to happen. Well, that's unfortunate that that's right there. So now we have arrows that are inside of the focal length. Okay, so our object is less than the focal length. We're going to do the same thing that we always did. We're going to go bounce the arrow to the parallel into the focal length, okay? Because now we can. We're not sitting right on top of it. And then we're going to do our second arrow, okay? And in this case, we're going to go through the focal length here like normal. So if it were on this side, it would go through the focal length and then parallel. Here, we're going to go through the focal length this way. We're also going to extend that arrow until it hits the mirror. Once it hits the mirror, just like always, it's going to go parallel. So these last two have been a little bit different. They're a little tricky. We're going to go always through the focal length, okay? But because we're projecting it that way, we have to extend our ray the opposite direction as well. Once we hit the mirror here, we bounce that way. Now, what I want you to notice here is these two arrows are diverging. okay? They are not going to be getting closer and closer on the real side of the mirror. But if I extend my arrows into imagination land, into the virtual world, okay, we're going to extend it into imagination land. All right, so I extend this red arrow, still following the same line, and I extend my blue arrow, following the same line. I do have an intersection on this side. So that's where I would put my object. Now, it's above the primary axis, so it's going to be upright, but it's also not a real image. A real image is going to be on that left-hand side of the concave mirror. So it's going to be virtual, upright, and enlarged. It's a much bigger object this time. So then when I go to fill out my chart, virtual, upright, and enlarged. So here's our last one. Now, this is not a concave mirror, but we follow the same rules as always. Follow the same rules as always. We're going to start out, we're going to go parallel and then through the focal length. Parallel, through the focal length. But remember, this is a mirror. So when it bounces, it's going to bounce up. But when I extend my line, it would go through the focal length. Then I'm going to go to the center point, a little bit different, kind of like what we did when the object is on the focal length, to the center point, and it's going to bounce off again. Okay. Do I have an image on the left side, on the real side of the mirror? No, I don't, because these lines are diverging from each other. But if I extend them into imagination land, I'm going to extend my red line again through that focal length, extend that blue line. I'm going to get an intersection here. And that intersection, I'm going to have an object. Is it real or is it virtual? It's going to be located inside of the mirror. It's not going to be something that can be projected from the mirror. So it's going to be virtual. Then it's going to be upright because it's got the intersection above the primary axis. And it's going to be reduced. So it's slightly smaller than this one was. And this is how it works for all convex mirrors. All convex mirrors are going to be virtual, upright, and reduced, no matter where that object is. It could be very, very far from the center of curvature. It could be very close to the focal length. It doesn't matter. All objects in a convex mirror will produce a virtual image that is upright and reduced. So we can finish out our table. Convex mirror, virtual, upright, and reduced. So then we have this concept of magnification. How can we get an idea of this mirror with this focal length is going to magnify this object or minimize this object based on the position of that object? We have a formula for that. And we've got a couple different ways to show it. Magnification M is going to be equal to negative Q over P, where Q is our image distance, our object distance. I don't really like to think about it like that. I like to think of it as distance that the image is located, okay, from the mirror, and distance that the object is located from the mirror. Or we have the height of the image versus the height of the object. Either way, this is just a simple proportion, all we're doing. If I find that my magnification is positive, that means that the image is going to be upright and virtual. If it's negative, that means that the image is going to be real or inverted. So my mirror equation, I've got 1 over DO, 1 over the distance of the object, plus 1 over DI is going to be equal to 1 over the focal length. So I just need 2 of these variables and I can solve for the third. So let's do an example real quick. I've got a concave mirror that has a focal length of 10 centimeters. Locate the image of a pencil that is placed 30 centimeters from the mirror. So what we're looking for here is what? We're looking for the distance of the object. We know, we're looking for the distance of the image. We have the distance of the object. Okay, we have the distance of the object. We're looking for the distance of the image. We have the focal length. So I need to rearrange my formula so that I can get distance of the image alone on its own side. So I'm going to do that by subtracting 1 over DO to get it to the other side. So now I've got 1 over DI is equal to 1 over F, my focal length, minus 1 over DO, which is the distance of my object. From here, I can plug in, and I can go 1 over the distance of my image is equal to 1 over 30 minus 1 over 10. I think it's easiest at this point to plug that into my calculator. So I can say 0.03333 repeating minus 0.1, and that's going to give me a value of negative 0.0667. From here, I need to get DI by itself. So actually, what I would do is I would multiply both sides by DI, and then I get negative 0.0667 times DI, and then divide it by negative 0.0667 to get that over here. I'm just going to take the inverse of it, and that's the same math property there. So I'm going to go DI equals 1 over 0.0667. This is negative, so I get DI equals negative 15. That's my magnification, is negative 15, or that's the size of the object, or the distance from the mirror is going to be 15 centimeters from the mirror. My original object was located at 10 centimeters. My focal length was 30 centimeters. My image is going to be found at 15 centimeters. Well, then I can go in here and I can say, okay, well, what's the magnification of my mirror? And in this situation, again, it's just a simple ratio. So I've got DI over DO is going to be my magnification. My DI was at negative 15 centimeters. My object was at 10. So I put in the wrong number here. So DO is supposed to be at 10. So my magnification would be negative 15 over 10, which when I work that out right here on Edpuzzle, 15 over 10, I'm going to get a magnification of negative 1.5. So you guys have to complete the ray diagramming worksheet for the rest of the class today. This is going to be due on Tuesday at midnight. Tomorrow, I'm probably going to be doing some stuff with lenses. I haven't really decided yet. But this Edpuzzle will be an assignment in the gradebook, and this will be an assignment in the gradebook. Your table, I want you guys to keep for your notes. Okay, so not this thing. Where'd it go? This thing. This I want you to keep in your notes. Very important that you kind of have this to kind of look back on and summarize and say, okay, if the object is located at the focal length in a concave mirror, there's no image, period. Hope that you guys have a good day. Wish us luck at regionals, and I'll see you guys on Wednesday.